Welcome, everyone. Thank you for taking the time to join us in our discussion today. I am your host, Hunter Wiley, and today we will be discussing some of the fundamental terms and definitions of ultrasonic flow measurement. In addition, we will look at how this ultrasonic theory is applied across our portfolio of Panametrics liquid flow equipment. A little about myself. My name is Hunter Wiley, and I am the Panametrics Global Services Training Leader. Prior to this role, I served as a field service engineer across North America for 4 years, servicing products across the Panametrics portfolio. Before that, I received my Bachelor's of Science in Petroleum Engineering from the University of Houston. I'm extremely honored to be speaking with you today. As the Global Services Training Leader, I have modified the content we will be discussing from our instructor-led training courses. These courses allow for a strong understanding of our equipment for technicians, engineers, and supervisors, and are customized based on the relevant field equipment in use at your specific facility. Our experienced trainers combine proven teaching skills with hands-on application for a highly acclaimed learning experience. For more information, you can visit panametrics.com/training. Before we go any further, I would like to take just a minute to offer a brief safety moment. During these ever-changing times, it's important to focus on your physical and your mental health. Like many of us, you may be stuck behind a computer screen at your home, while others may be continuing to operate at facilities. Wherever you may be, please be sure to stay active. Take breaks to move around, perform stretches at your desk, and even take a walk if you're able. Find a way to connect with others. That may be through telephone or video calls to your family, friends, and even coworkers. Be sure to eat well. This is one that I'm personally working on. Meal prep may be a hassle at first, but it will pay dividends throughout the week. And finally, get some sleep. Find a way to limit your screen time, and especially for those of us working from home, ensure you hold to a set time so you can leave work. A quick history of Panametrics before we get going. Founded in 1960, Panametrics started off as a moisture measurement company. Though ultrasonic transducers were developed in the late 60s for non-destructive testing, Panametrics repurposed the technology for transit time flow measurement in liquid applications. Since that first commercial flow meter in 1979, Panametrics has continued to revolutionize ultrasonic flow measurement in various process conditions, while simultaneously growing its initial aluminum oxide probe hygrometer into a full portfolio of gas and moisture analyzers. Many industries recognize our legacy of excellence and our ability to provide solutions to even the toughest applications. We are Panametrics, a Baker Hughes business. We will begin with some fundamental terms and definitions that are used in ultrasonic flow measurement. But before we get into that, what is ultrasonics? To get that answer, let's take a look at the different types of sounds. Sound waves are vibration energy that travel through gas, liquids, or solids. Sounds can be classified by the frequency ranges as shown on this page. The most common sound waves are those that we can hear. These sounds fall in the range of frequencies between 20 Hz and 20,000 Hz and are called acoustic or auditory sounds. Sounds with frequencies below the acoustic range are called infrasounds, while sounds above the acoustic range are called ultrasound. An example of infrasonic sound waves is the communication of whales. These animals send sound waves through the water across many kilometers using a very low frequency sound wave. Baleen whales in particular use a bristled plate to generate these deep sounds for tasks like location, migration, mating, claiming territory, and more. When it comes to auditory sounds, us humans are quite familiar with what these sounds are like. We use sound waves every day in this frequency for many uses, such as to detect things like a falling tree or an approaching car. Of course, another very common use of audio sound waves is in normal conversation where one person speaks and the other listens. Ultrasonic sound waves have a higher frequency than infrasonic and auditory sound waves. Dolphins use organs in their forehead to emit bursts of ultrasonic sounds and then listen to how the sound bounces back to them. The relatively higher frequency of ultrasonic sound provides an echo that has a higher resolution. This resolution enables the dolphin to distinguish between a fish, which could be its lunch, and another object like a floating piece of seaweed. From the title of this section, you likely know by now that Panametrics flow meters utilize sound waves in the ultrasonic frequency range for sounds. But how are these sound waves transmitted? Sound waves rely on a process or a medium to move from one point to another. The definition of this process depends on its state of matter. In each of these states, the sound wave has to jump from molecule to molecule. The closer together these molecules are, the quicker and the better the sound wave can be transmitted across that medium. For gas processes, these molecules are spread far apart. This is considered a relatively low density process. As we look at liquid, the molecules are closer together, allowing for more signal to easily traverse from one side to the other. Now on the right of this spectrum, we have the solid materials with their molecules packed tightly together. While this state of matter has the highest density, it can allow for the best transmission of sound waves. Now, I should mention that each of these states of matter fully depend on the specific molecular structures, temperatures, and pressures to define the density of a specific process. That is why a gas process with hydrogen does not typically allow as strong of a signal to be transmitted through when compared to a similar volume of natural gas. Similarly, the same can be said between a heavy liquid crude oil when compared to wastewater. Density also plays a role in the characteristic sound speed of a process. Sound speed, or how fast a sound wave travels through a material, depends on many factors, but tends to change with the state of matter and the process conditions. In general, for gas applications, sound speed will increase as temperature increases. Alternatively, many liquid sound speeds tend to decrease as temperature increases. Of course, there are always outliers, particularly in this case, water. Up until 74 degrees Celsius, or about 165 degrees Fahrenheit, the sound speed will increase in water. Above this temperature, however, the sound speed will begin to decrease until the water vaporizes. On the right of this screen, you can also see a list of some sound speeds for various processes. Note that the sound speed in liquid water is over 4 times that of the sound speed of air, and the sound speed of solid stainless steel is more than double even that. Just from seeing these different sound speeds, you can see how density of a process affects the transmission of an ultrasonic sound wave. But what else can affect a sound wave? Now that we know how sound travels through materials, it is important to know that there are 3 distinct ways we can lose this signal. In ultrasonics, these 3 methods are collectively referred to as attenuation. The first one, dissipation, occurs as the ultrasonic wave propagates through a medium. Take, for instance, the ripples that are generated when a pebble falls into a still pond. The farther the waves travel from the initial source, the weaker they become until they're not even distinguishable from the rest of the water. This method of attenuation is most common with hydrogen-rich processes. As the signal tries to jump from one molecule to the next, the overall strength of the signal decreases rapidly. Reflection occurs when a sound wave bounces off of an object. We can see this in action when we hear an echo as the sound wave bounces off of a wall and comes back to us. In ultrasonic flow measurement, we can actually bounce a signal off of the opposite side of a pipe to be able to get a flow measurement. However, reflection is not always our friend. Second phase materials, such as a solid catalyst in a flare line or gaseous bubbles in an oil pipeline, can cause the signal to bounce away in a different direction than what is expected. Absorption occurs when a sound wave is absorbed by a material until it is reduced or even lost. Some materials like this may have rough or even porous surfaces. A soundproof room is where there are many of these layers of materials that absorb the sound wave. In ultrasonic flow, this can be observed with process buildup, corrosion, or even some attenuative gases, such as carbon dioxide. Each ultrasonic flow meter by Panametrics has an automatic gain control, or AGC, which controls the amplitude of the transmitted signal to compensate for attenuation in varying flow conditions. However, there is always a point where too much attenuation is simply too much to overcome. With those fundamental terms and definitions aside, let us look at how a Panametrics ultrasonic flow meter operates using this transit time theory. Let's first look at how the signal is generated to start with. We utilize the piezoelectric effect, which is the ability of a certain material to generate an electric charge in response to an applied mechanical stress. In Panametrics ultrasonic transducers, we use this phenomena for signal generation and reception. Piezoelectric materials are characterized by a relationship between voltage and mechanical energy. An ultrasonic sensor uses this characteristic to both generate and detect sound waves, as illustrated on this page. When the transducer is transmitting, the circuit will close and be completed, causing current to go to the transducer crystal, exciting it, causing it to vibrate and generate these sound waves. On the receiving end, the receiving transducer is listening, so that circuit is closed and completely listening until that sound wave strikes the crystal, causing it to vibrate, and then that vibration is turned into electrical energy to be returned to the meter electronics. As you can see in this demonstration, the sound wave is generated by one transducer, travels across the process, and is received by the other transducer. That second transducer then transmits a separate signal going back across the process, where it's then received by the first transducer. You can also tell by this illustration that the velocity of the process flowing through the pipe will affect the total transit time in each direction. When the signal is going in the same direction as the flow of the process, the signal goes faster when compared to the signal going against the flow. These transit times in each direction are used to calculate velocity, which we will look at in just a few minutes. In addition, both transducers are required for flow measurement. Just like you need two people to have a conversation, we need two transducers to talk back and forth for flow measurement. When talking about clamp-on transducers, the transducers are named with regards to their relative location to the direction of flow within the pipe. Let's take the example of flow going from left to right. The transducer that the process passes by first is known as the upstream transducer. Its matched pair, which sees the process pass by second, is known as the downstream transducer. Even for applications where the transducers are on the same side of the pipe, using multiple traverses, this concept still applies. The lateral distance along the pipe from the center line of the upstream to the center line of the downstream transducer is known as the spacing. Each of our liquid flow meters utilize Snell's law of refraction to calculate this spacing for you. The meter will require the size and material of the pipe wall, in addition to the same parameters if a liner is installed inside. Certain transducer parameters, including frequency and signal angle, are also taken into effect in the calculation of this spacing parameter. Now, bear with me. I know there are a lot of terms on this page, but we're going to talk through each of them. What you see here is a typical wetted liquid installation. We call it wetted not because liquid is wet or anything, but rather because the transducers are physically in contact with the process that's inside the pipe. These follow the same naming conventions as the clamp-on transducers do, with the upstream transducer being the one on your top left and the downstream being on your bottom right. The time it takes for the signal going from the downstream transducer to reach the upstream transducer is known as the transit time upstream, or T-up. The time it takes for the signal to go the opposite direction, or with the direction of flow towards the downstream transducer, is called the transit time downstream, or T-down. The flow meter will need to have the path length, P, entered as a known fixed value, so proper sound speed and flow velocity can be calculated. This is the distance from the face of one transducer to the face of the other one. In addition, the axial length, L, is the measured distance along the direction of flow in the pipe between the two transducers. These two dimensions, P and L, are used by the flow meter to calculate the angle of attack and to determine the velocity of the process that's flowing through the pipe. Other parameters to note are the outer diameter, or OD, and the wall thickness. These two fixed values are entered into the flow meter to calculate the inner diameter. For a circular pipe, this ID lets us calculate the cross-sectional area, which then allows us to find the total volume of liquid that's flowing through the pipe. One thing to note is that this is the actual volumetric flow rate. For many customers, actual volumetric flow is sufficient. It may be in liters per minute or gallons per hour, but this would be sufficient for many applications. For customers who have processes that tend to change significantly in densities and volumes based on pressure or temperature, we can also take those parameters as inputs into our flow meter and compensate those for a standard volumetric flow. So how do our flow meters use transit time to calculate velocity? If you're like me and find enjoyment in a complete set of derivations that lead to a final formula, feel free to take a look to the right. But if you think I'm a little on the weird side for liking formulas the way I do, please just forgive me and remember I'm still an engineer. Ultimately, the entire basis of transit time theory depends on comparing the transit times in both directions. If both the upstream and the downstream transit times are equal, then there's no flow present. As flow begins to increase, the T down value will be smaller than T up, resulting in a positive velocity. Another calculation that is obtainable through transit time ultrasonic flow measurement is sound speed. As we mentioned before, sound speed is simply the velocity of a sound wave through a given medium. In this case, we can look at the sound speed as the distance the sound wave travels in a known time interval. Our distance is a fixed value, that's your path length or your P parameter that we discussed earlier. The time is simply the average of your two transit times. As a word of warning for those of you that want to check my work or do these calculations on your own, you need to ensure the units and scaling all match up. Units of velocity and sound speed are typically in feet per second or meters per second, while the units for the path length are inches or millimeters, and units for transit times are typically in microseconds. The next calculation our flow meter will perform is the volumetric flow measurement. To get this, the meter simply takes the actual velocity that was just calculated, then multiplies in the cross-sectional area of the pipe. In many cases for liquid flow, as most liquids are not very compressible, actual volumetric flow is typically all that is required. But if local regulations or certain process requirements necessitate standard volumetric flow measurement, a live temperature and pressure input may be required. These, coupled with the desired standard or base conditions for temperature and pressure, are used to normalize the actual volumetric flow to standard conditions. In addition, when required, Panametrics electronics can accept conventional gauge pressure units and convert to absolutes as required. The last calculational parameter we're going to discuss is the mass flow measurement. Since all of these applications with the Panametrics liquid flow meters are on known density or known compositional lines, it is very easy to calculate the mass flow. Simply take the density of the fluid and multiply it by the volumetric flow. In all of our flow meters, you actually are able to use a fixed density as an input for the majority of these applications. Alternatively, if there is a variable density based on certain viscosities, such tables can be input on some of the higher end flow meters. Now that we have had some time to discuss the terms and theory, let us look at the equipment that is likely in use at your facility today. This slide shows each of the liquid flow installations that are available. Depending on the accuracy requirements, the process conditions, or even the accessibility of the point of measurement, Panametrics has a product that can measure your process properly. The high accuracy flow meters are in the Sentinel family product line. These are fully integrated flow cell spools with wetted transducers. We have a few images coming up showing just how these transducers are installed in their respective flow cells. Many customers utilize these for leak detection and custody transfer in pipelines and many other applications around the world. They can be designed to handle cryogenic temperatures if required and provide a wide set of parameters defining the full flow profile. This is due in large part to the vast number of channels and measurement paths that these meters have. The Sentinel LNG and LCT4 have 4 paths each, while the LCT8 has 8 measurement paths. The PanaFlow products are also wetted installations that provide a robust flow measurement in many applications. The PanaFlow HT on your far right is the world's first ultrasonic flow meter to be SIL certified. These are typically used on coker distillation, vacuum towers, or any other safety critical application. The PanaFlow Z3 system builds on the same cast body flow cell styles of the Sentinel product line and utilizes the new XMT1000 electronics. This next generation meter improves on the XMT868i by offering a faster response time, more diagnostics, and the ability to measure up to 3 flow paths. All of the previous flow meters required a manufactured spool piece to be dropped into your line. If your process does not allow for the line to be brought down, or if you need a more temporary installation, you may elect to go with the clamp-on systems. The PT900 uses a tablet interface and can measure liquid flow in many different processes. It recently replaced the PT878, an industry workhorse, and it continues to provide quick spot measurements with a short installation time. In many locations, a flow reading can be obtained in as little as 10 minutes, and that includes the setup, programming, flow measurement, and removal of the equipment. The AT600 steps into the industrial water measurement market with its IP67 enclosure and advanced diagnostics, mirroring some of the capabilities of the Sentinel flow meters. The XMT1000 has also been updated recently to provide support for liquid clamp-on systems, allowing for an easy field upgrade for existing clamp-on liquid flow systems on cooling towers and wastewater facilities everywhere. Liquid clamp-on transducers come in many different shapes and sizes, but all are compatible with each of our clamp-on products that we mentioned earlier. For smaller pipes, the CFLP integral transducer mounting bracket allows for easy spacing, measurement, and placement. Additionally, the other integrated rail just to your right is what is used for the AT600, allowing for a quick, easy, and consistent installation. Some may recognize the transducer in the bottom right corner. This is the CET transducer system, a clamp-on solution for high-temperature applications. Other notable transducers are the CRS 401 and 402 transducers that you can see in the middle, commonly used across a vast majority of liquid applications. Wetted transducers for applications are used in both the PanaFlow and the Sentinel product lines. The WT and BWT transducers on your left are used in higher temperature processes in conjunction with various buffer assemblies to allow for measurement in extreme temperatures. The two images on your right-hand side show the way the integral transducers of the LCT4, LCT8, and the PanaFlow Z3 fit together inside the cast body flow cell. A small insert on the far right-hand side provides the pressure boundary, allowing the compact transducer behind it to be removed without requiring the line to be brought down, reducing potential downtime. Here you can see a clamp-on installation of CRS 401 transducers used on a relatively cold process. Even during harsh weather and extreme external conditions, our clamp-on flow meters can provide reliable service in many applications. And I'm just going to say this, contrary to popular belief, the image on the right is not an octopus. The armored cable of this XMT868i flow meter allows for installations to be used in a wide variety of area and certification class ratings. Because of this, armored cable is preferred for this very reason in many locations around the world. And with that, I would like to conclude our discussion today on ultrasonic theory and Panametrics liquid flow equipment. Thank you for your time and for joining us. Should you have any further questions regarding training, products, or more, please let us know how we may be able to help you at your site. Please stay safe, and I look forward to speaking with you again soon. Thank you.